we are keeping it here. We'll keep it.
Okay, so wake up call is already there. So what I am supposed to talk about is the interferometric detection technique. Nobody is also going to talk about in future in this school. So I thought that first thing that we will do today is that I'm sure if you know about it. And, I thought still that first thing we will do today that we are trying to detect with the interferometer. Okay, and they are in the same page with that. If there is enough time at the end of the lecture today, we'll first see that what is the basic what is called testing with interferometers and the power spectrum detection. But then we'll ask the question at the end of this talk that what are the canonical techniques and what are the things that we want to look at particularly for this application. Very large, very bright signal which is the foreground. Okay. So that is what we will, that is the plan for today. So anytime you want, you should stop me, and I'll probably go and then at the beginning, before doing anything, we'll find a few things to confuse. Okay. The first thing that I will like to keep in temperature, which you have heard and know about. The spin temperature, remember that you have a, you can call it a zero level and call it is that you have some number of atoms not change really, but we'll write it in a different way. So I will define Ts. So by the way, this G1 is how much is G1? Kanu talked about it. And G0 is 1. So this is essentially 3. Right? This ratio is 3. And how much is nu 0 by kb? 0.068. So that I can call it to Ts. Natural logarithm of 3 n1 n0 by n1, right? So again, that's a definition. What it is doing is it drives intensity. It is the amount of energy following the detector, following in time, following in area detector, and coming from a given solid angle. So following of that solid angle. So that is intensity. It is just writing that intensity, and that's it for the brightness temperature. You always try to write everything in terms of temperature is obvious because then you can compare those. Okay. If I have a thermal emission in the Rayleigh limit, then the intensity of emission, intensity of that black body in the Rayleigh limit is this. Okay. So that is related to temperature of that black body in this way, but otherwise for any intensity. So this intensity to the synchrotron emission that Saurabh was talking about, I can still write it in a temperature unit. And these are just that. Okay. So this I wanted to keep here because these are the things that we will encounter at this. The other thing is known cosmological parameters like H0 and the omegas. Okay. So once you know that, so when I write R, the observing frequency. If you look at this, so this lambda is also. Now if I want to write it in terms of the 21 centimeter wavelength, so if I observe in a case of 21 centimeter outside, how will that lambda to be this lambda? That will be redshift of 9. It becomes the redshift of 9, right? So that if I write lambda 0 as C, if I write lambda 0 as I will have to put that correct factor is 1 to get it to the observer. So if I observe redshift from which it is coming, because nu is redshifted from the frequency 1420 megahertz, and then I can figure out for that redshift what will be the co-moving distance. Okay. If you are not, half of you are not familiar with how to calculate the co-moving distance, the other half is familiar with it, so the other half can teach the half which are not familiar. Alright. So with this, so let us ask the question now. So what is the signal that we are trying to detect? repeat the question here. So what is that we want to detect? Using the interferometric. So kind of test we have already seen today when Prasun and even later Shaura was talking about the evolution of the 21 centimeter signal. So let me just put a very rough picture of it here, and let me not put the rough picture. We put a cartoon here. All that we can detect in terms of photon, the further in the in first is coming from what is called the last scattering surface, where from where the CLB originates. The photons were last scattered with the electrons at that surface. After that, the electrons recombined, so you don't have any scattered. So the CLB is all coming from there, right? So that's the cosmic microwave background radiation. And then again, so that radiation will have an intensity, and for that intensity, I can define a temperature using this. And that temperature from the CMB, I will write as T gamma. Gamma, I don't know, it doesn't do much justice to the microwave background, not gamma rays, but this gamma basically tells you that it is related to the photon temperature. Now, as you know, that if I look at different direction in the sky, T gamma will be a very slightly different. It's 3.2.732 Kelvin in an average in every direction in the sky, but on top of that there is fluctuations and 10 to the minus 3, 10 to 10 to the minus 5 level. Right? So this T gamma, then you can say that this depends on the direction in the sky. So the direction in the sky I will denote with n cap. N cap is a unit vector which changes in different directions in the sky. How many numbers do I need to define an unit vector in 3 dimensions? How many independent numbers? 3. 2. 3 numbers to define a vector, but because it's a unit vector, I need only 2. So this you can think of as theta and phi. Like when Saurabh was writing, he was writing in terms of theta phi. So if I want to write an integral over d n cap, which is infinitesimal unit vector integral, so that can be sin theta d theta d phi. Like that. I can write the same integral in terms of the direction cosine, and in terms of the direction cosine, this is this. So these are different components. So this is here I will call it d omega. So that the different components of omega is theta and phi. Here the components are L, M, and N, where obviously L square plus N square plus N square has to be. So that is T gamma, and then in between I have the H1. That is my model. Now, what will the H1 do? If you remember what Prasun was talking about, I will not even write down the ready to transfer solution, but if you think, what it will do is it will absorb part of the CMB, right? And then it can emit. So if I said I will not write down, but if I write down the brightness temperature at a given direction after it passes through the H1, so it will be T gamma, but then T gamma can get absorbed by this H1, so it will depend on the optical depth of H1. And then again, so what I am writing here is very rough, because it only is true if the H1 density and the spin temperature is constant in this. That's a very thin one, but just to understand things, write it down. So what it will do is, it will absorb that thing which is coming from the CMB. Then there is an emission term, which is the emission from the H1 itself, which is S nu. But you can think of the amount of H1 which is getting emitted from this part of the cloud will get absorbed as it goes through. So that's called self-absorption. So that is the second task. Check out the amount of absorption that has happened within the cloud. That's a very crude model where things are not changing. Of course, this cloud and the cloud is steam, etc. But to understand, so that's what will happen. So this is what I will reach. What I will reach us. That is what we'll try to write a model for this brightness temperature. Okay. So this, I think, Prasun will work it out. Prasun said that he will work it out for you. So I will just write down the model is this. Let me write it down and then I will discuss about different terms. Okay, so let me first let us first discuss what we have written down so far. So when I write delta TB, this is the fluctuation in the temperature at different directions. So there can be a mean one. Like I said that for the CMD it is 2.732 Kelvin, if I just look at this. And on top of that there are fluctuation in different directions. Right? So I'm not really looking at what is the mean, so I'm just writing the mean signal is what Saurabh is talking about. Well, we are talking about the fluctuation on top of that mean. And we'll see that. And I think that Girish will talk about the cosmological information in that. But anyway, so this is the delta TB, which is the fluctuation over the mean which we are talking about. It will change at different directions, so that's why we call it fluctuation. Obviously, it will change with different Z. This signal actually, if you look at over the cosmic epoch, it can be negative or it can be positive. In the sense that I can see the H1 in absorption, I can see H1 in emission. But the part that you will be interested in is mostly the H1 in emission, this epoch of reionization and thereafter. Then I have this quantity which only depends on Z. This also has a dimension of a temperature. Okay. And once I use all the cosmological parameters that I know, so like this is calculated with omega baryon H square as 0.02 and small h as 0.7. Remember that small h times 100 is your Hubble constant, 0 to 70. So then you get a value 0.4 millikelvin into 1 plus z square. You also have to take care of this factor, and again half of you can teach the rest of the half how to write down h as a function of z from the standard cosmology. That exact thing you will also need to calculate this quantity as a function of z or function of the observed frequency. So that's all. So again, if you can look at this, so this has all the things which are related to the standard cosmology, and this even is not a function of n cap. So this is the thing. This is a number which is constant across this time. All the variation in n cap is there in this quantity. So let us define this quantity. This quantity actually tells you how the signal, that the brightness temperature varies at different directions. So this we will call the 21 centimeter radiation efficiency. You can see why it is called an efficiency. This is something which is multiplying the temperature, right? If all the direction the n cap, this thing, imagine that this thing is 1. It doesn't depend on n cap. So then your delta TB will be just theta. This essentially is telling you how it is changing in different directions. So let us write down the expression for this, and then I have given you the reference in paper where all these things are calculated, and Kanun will do part of it. So I will just write down these results because this is what we will need to go forward. So this, and the important thing to realize is what does it depend on. Let me write down all those things. Okay, so again, so let us go through different terms. So this term you can see tells you the difference in the spin temperature with respect to the temperature of the CMB. So in this case, as I said, this will be in emission, so spin temperature has to be higher than T gamma. I think Kanun will talk about it tomorrow, where he will go through the reionization, the post-reionization. So this is the difference in Ts and T gamma. I have just written the S cap and Z dependence here, but we can think that it can go through all these terms. The first term, rho H, just gives you the density of the H hydrogen atom. But then all hydrogen atoms are not neutral hydrogen atoms. Some of them are ionized. So the top part is the density of the neutral hydrogen. You can think of this ratio as how much of the hydrogen not ionized. And then this term comes for the fact that, so let me write this down. So this is called, this is a peculiar velocity term. This is difference in CMB and T spin, and this has the information of how much neutral hydrogen is there. And all these terms, all these three terms can vary across different directions in the sky. And of course, can vary with the redshift. So why there is, what is a peculiar velocity term? Well, you know that if we look at the sky, everything, if we look at a galaxy, is far away, moving away from us with a velocity that you can calculate just using the Hubble law. But depending on the density structure near to that galaxy, density structure of the universe, that galaxy may feel a local attraction or repulsion. No repulsion, but repulsion in the sense that there can be things outside which can pull it out of that body. So that velocity of that galaxy will add up on top of the velocity because of the Hubble law. So that's called the peculiar velocity. And when you say that, okay, I looked at that galaxy, what all I measure is not the velocity but the redshift of a spectral line that galaxy is emitting. In this case, the 21 centimeter line. Now, the shift in the 21 centimeter line, part of it or most of it for high redshift will be because of the cosmological redshift, but part of it will also be because of its own velocity. That part is taken care of here. All these calculations are there in that paper. Again, I have given to you in the classroom. You can have a look. So this is essentially the thing that we will be more interested in, because this is something which changes at different directions in the sky. Now, the experiments that Saurabh is going to talk to you about looked at the global signal. The global signal is that where you will think it doesn't change the direction in the sky. Average over the. What we will be interested in is to look at this changes in different directions in the sky. There is a good reason for that. The global signal is more, I will say, more difficult to detect, but part of it may be already detected. More difficult to detect because the measurement equation that Saurabh was writing down has a noise term, and because you are looking at the same part of the sky only with one telescope, you have to know that noise term very well to get signal above that noise. That part for the interferometers is a little easier to handle. And then again, there are informations in this signal, like for example, we will look at the peculiar velocity itself, which are not there in the global signal. So I think we should talk more in the galaxy formations, etc., and the later epoch of reionization. So those all informations about those can be extracted from this. So we'll now, from now on, we'll look at this. So the motivation to write this down so far is that you see that this depends on how much neutral hydrogen is there at different directions in the sky, how the spin temperature varies across the sky, the velocity changes across the sky, etc. So this thing has all this information, and you want to extract it out. Now, how do I extract it out? Well, of course, this is the thing that one can measure, because this is the thing which is proportional to the specific intensity by this relation. Now, the brightness temperature, that is here, time to measure. And then you immediately see this eta is multiplied by a number which is 4 millikelvin. And how much was Saurabh telling you is the foreground? In Kelvin order, much more than. So it's a very tiny signal that you are looking at. So because it's a very tiny signal that you are looking at, if I ask you, take a telescope which will make a map of this in the sky, map in the sense that it will measure delta T a different direction in the sky, that will almost be impossible. So what do? You do not look at this signal, but you look at the statistics of the signal. And it turns out, you know, in cosmology already, at least from the experiment of CMB, that the statistics of this signal, statistics of the temperature fluctuations across the sky, has a lot of information still remains there in that. And so that is what we will look at. And how to look at the statistics is basically what I am supposed to tell you. We remove things here. So before we look at the statistics there, again, I suppose that you already know a lot of these, but still, there is no harm. So let's say that, so here is a field which is same different in different directions. This thing which is I have written as Z, which is the redshift, I can read the redshift also as frequency, right? Because for a given redshift, the 21 centimeter comet is given frequency. So I can also read this as a frequency. But for the time being, let us forget about the frequency dependence or the redshift dependence. Let us say that we are looking at the signal which is coming from given direction. Of course, we have set Z to something. Set the Z to Z equals to say 5 and 40. So looking at everything from Z equals to 5. And let's say that not given temperature, let's say any scalar signal which depends on a direction n cap, and there is no harm just for the sake of understanding to write it this way. So that's what I have written here is any scalar field which is a varies with three numbers. It's a function of the three-dimensional vector. And I say that I cannot measure this, but the statistics of this has enough information. How do I define those statistics? That's the question. You want to do the statistics. One thing obviously, you can measure the mean of the signal or the standardization of the signal. Those are the two numbers. And you can imagine that those are also kind of globally average numbers. The mean is that you have integrated over all possible directions, all possible x in standard deviation is squared and then integrated. Squared subtracted the mean, squared and then integrated. But more interesting are the 2-point statistics. Turns out that a lot of information also is written there. So one of the measure of the 2-point statistics is called the 2-point correlation function of the signal, which if I write, it can be defined this way. Okay. Change things. Okay. What we have done here, so we have multiplied the value of A at two different x's, and then we have written this square bracket, which is an average, and this is supposed to be an ensemble average. The idea is that all the signals that we are talking about is stochastic in nature, changes at different directions, apparently random. And here, at least, this is an hypothetical case of truth, not directly related to what we are talking about there in that part of the board. But if I have such a signal and I have many realizations of this signal, I can have an ensemble of that signal and I can take this average over that ensemble. For every ensemble, I calculate this, then I average it over the ensemble. Once I do that, I get a function psi, which is a function of x1, which is an ensemble average. But then I can say that, okay, maybe the statistics of this is independent of where I choose the origin. If that is the case, for the statistically homogeneous system, I can write this now. Okay, you may ask how, but it's very straightforward to see. This is, instead of writing it in terms of x1 and x2, I can write it in terms of x1 plus x2 by 2 and x1 minus x2. x1 minus x2 is essentially r, and x1 plus x2 by 2, the signal should not depend on that. That I have already said, so that it does not depend on that. You can do even better. I can say my signal is not only homogeneous statistically, but it's also statistically isotropic. So it even doesn't depend on the direction of the vector in either way will give you the same number. And still you are averaging over the ensemble. But then now if you look at try to estimate this from a real sky signal like this, you tell me that, well, I have only one sky to look at. I don't have many universes to go to and calculate this ensemble average. So what do? You assume that different part of the sky has the same income. Of course, I will not be able to average over the sky when I am looking at a scale which is as large as the sky, where I have only one information. But then I look at or in this case, you can come back to n cap, which is much smaller than two exactly opposite directions in the sky. So then I can replace this average essentially to the average over x, the two different origins average. So then internal average can be replaced by a spatial average because that the signal is orthogonal. So that's what we do. We try to estimate the 2-point statistics of this signal, averaging it over different directions in the sky. So let me then take this out also. This is essentially what we use. Now, there's another way of representing this. And represent this as in terms of the Fourier coefficient, where I define this as, to be careful in defining it, because I want to be consistent. Basically, the Fourier three-dimensional Fourier transform of that. And then I can define, as parallel to this, I can define a quantity called power spectrum. Okay. Three-dimensional Dirac delta. This is the definition of this. Yes. So tilde I have defined, I have used to define the Fourier transform. Now it turns out that I am not writing it down. So these two are again Fourier transform. The Fourier transform. A and Z. Okay. I'll get you to sync in with that. And then what we will do next is change A with replace A with this thing. I want to calculate the power spectrum of theta H. That is nothing. I'll stop a little bit here and if you have any questions. Why you are doing Fourier transform? Who asked? So that's a good question. We will see. It's easier to measure the Fourier in the Fourier domain, not in the. That's how the interferometer works. So it will see at the end we will establish that this quantity will be directly related to the visibility that the interferometer. So I'll remove this part of the board. I really is not anymore interested in how this is related to the other things because this is a signal that I will work with. The only thing that I want to know now is the 2-point statistics of this signal, H1 as a function of n cap and z. Anything else? Question? physically what it means? It's a good question. So let us. Okay. So do you understand what does this mean physically? Right. But what does correlation mean physically? Right. So if I have, so forget about that's a two-dimensional thing. So let's say I have A, which is a function of one number only. And let's say that that number is T time. Okay. So when I write this quantity, okay, what is it telling you? So imagine that this number is completely random in time in so extent that you know that this value at one time, there absolutely is no way of knowing what is the value at any other time. What do you think this multiplication will be? Every time you take another example, it will be something else. And if this signal has zero mean, it will be zero. So anyway, this is essentially telling you how much that you can predict the signal at any time. So this a plot in case of a time signal itself, it will show something like this most of the case. What does it tell you? It tells you that at tau equals to 0, obviously, it will be predictable. But then as you go ahead with t tau, at some point it becomes completely unpredictable. In case of this is the electric field of an electromagnetic wave, tau as is close to certain value of zero, called the coherence time. So it essentially measures the temporal coherence. In this case, it will measure the spatial coherence. The Fourier transform. Okay. So then we have been writing this thing down in terms of the brightness temperature, but an interferometer measures something called visibility, which is roughly the Fourier transform of the intensity. The intensity is in this side of the brightness temperature expression. So now again, I will go back one step and then write down the intensity as what is measured by an interferometer, Fourier transform of which can be measured by an interferometer. So the intensity for the same signal that we had here, I'll just write it down once, and then you will see that part of it is again for calculation. Can we written this? And I1 new, so I request you to look at the reference that I've given you. I1 new is a combination of that KB, these things, because I am writing now delta T in terms of I, so this, all those things will come in. And then remember that there was a T bar there, so it will also depend on that T bar. So this point. Please go through, you can go through this, the reference that I given. From that you can look at it. So this is the brightness temperature. Sorry, this is the brightness or the intensity fluctuation at different directions, which is because of 21 centimeter radiation coming from a direction n cap, and z is the redshift from which it is originated. Now, let us ask the question that what interferometer see it here. So let's say this is my point of observation. Now, the interferometer, as you will see, is a collection of many telescope. Each telescope, so they are kept at different places on the surface of the Earth. Telescope means many antennas differently. So many antennas, collectively they are called one telescope. So they are kept at different places in the Earth. No, that is just because I want to relate something that my interferometer as a telescope measures with the signal that you are talking about. It measures directly a Fourier transform of the signal. This is this, see, all that you have to do is you have to put delta TV here and you have to calculate delta I from there. Now delta TV has that T bar, so that T bar and then combination of this will give you that I bar. And the rest of the thing is eta. So this is essentially, if I could have written delta TV proportional to this, instead of writing proportionality, I have calculated thing which I have not calculated, I've given you to calculate. So this is my observer, and then you are looking at a given direction this time. So let's call this direction. Now when I have a telescope, as Shora was pointing out, it does not collect signals from all this time. It only collects signal from a region in the sky. What is the reason for that? It has a definite field of view. Why it has a definite field of view? Why it has a primary beam? So let's say that what is a very basic receiver? So there is one in the next room, so you should all look at. There is a horn antenna, there is a ear antenna, and there is a dipole antenna. And what does the dipole do? Anybody remember how the dipole receives radiation from different directions?
So the angle, the direction in which the waves are, they should excite the antenna
Right.
the similar.
So if I have the dipole in this direction, the electric fields which are along this can only generate charge separation in this dipole. If the electric field is like this, it will not do anything along that line. Right? So there is a directionality of the dependence of what direction these things are coming in. And you put in a, if you once you put in a dish, for example, you improve on that direction. It can only detect in a given direction. So this will not only observe from this direction, but it will also observe a region. So if I now, so let's say that it will also observe how something is coming from there. And I call this small vector which separates these two. Just my nomenclature. Does that n0 plus theta is n. So n0 is kind of at the center of the region of the sky, which I call the field of view, where I can look at. And n cap is the particular direction with respect to that. So theta now spans over the entire region that I can look at using the telescope. Now the way the telescope that you will think of it operates, that it follows the sky, which means that this n0 direction always points towards a particular RA ray in the sky. So it is fixed with respect to the cosmological series. Now, I need to write this down. So let's write theta tilde is Z, which is the Fourier transform of theta. Need to have the Fourier transform triangle, right? Yeah. Or let me again write down and then explain. You see, this is just the Fourier transform of that. Only interesting thing that you look at here is that I have this R nu N cap. Why do I have it there? Because you see the Fourier transform is simply for I k dot x. So that k dot x has to be dimensionless because it's an exponential. So that x is nothing but a vector to that point where the signal is, where it is. Now, if I ask you what is the vector to this point, so if it is originating at a redshift z, then I can calculate at what frequency I will observe it. So 21 centimeter signal, supposed to be 1420, originated at redshift 9, so it will be now at 140.2. So that distance is again R nu. So that is the common distance R nu calculated. Vector that goes there is R nu times n. So that's what I have done there. So for the time being, it is just n. I have done that decomposition here. If I do that, so this is again just exactly the way I have defined the power spectrum over there. See, this is just the inverse relation. And let me see, I have to be careful. So here, this is plus this is minus. But anyway, I can then define what will this be? So just look at what we have done in A over there. It's the exact same thing here with theta H1. There's a proxy Z, but otherwise it is exactly the same thing. So this is 2 pi whole cube. 3-dimensional delta function, k minus k prime, and then the power spectrum, so this I call the H1 power spectrum. It will have, which is essentially having all the information for cosmology and then much more information. So that's the quantity that I am interested in measure. And see, k is a 3-dimensional vector, right? Now, the vector k composed in the following way. If I come to this, think of this as the coordinate. The coordinate is this n0 cap is the direction, is the z direction. Or this is also the direction, which is the direction of the average line of sight. Line of sight means the direction we are looking at. Obviously, if I look at different parts in this field of view, the line of sight is different, little different. But this is the average direction, right? So I can decompose this in terms of things, the k which is parallel to this will be k parallel n0 cap, and then the k that lies perpendicular to this line of sight direction is in this tangential plane in the sky. So that I will call k perpendicular. And you see over there is a k dot n cap sitting over there. What will be that k dot n cap? K parallel. Is that all? K, the n cap I write this way. What is that? The first thing will obviously give you k parallel. The second will give you k perpendicular times t. nice effect. Now, now, so this will come back to tomorrow again, but let me write down for you approximately what an interferometer measure is this. What is U, etc., so that we can debate about later. This thing is called visibility. So this will again and again. But this is an interferometer, what an interferometer measures. How it measures, etc. So we will see explicitly tomorrow. But then I have this thing, which is what Toda was referring to as beam. So it is the directional sensitivity of the antenna. As we said that we can only see mostly in this field of view. A theta is a function which is 1 at the direction we are looking at. We look at. And then as theta increases, we can assume for the time being it is isotropic in theta. That is, as theta increases in all the directions, goes down. Eventually it falls to 0. It has a finite support, which basically tells you that goes to 0 at a finite center of the field. So that is theta. Multiplies the intensity. The intensity is the intensity fluctuation, the same intensity fluctuation that is written over here. But you see now it is written as a function of theta. Why? Because remember, I said that if N0 cap is fixed with respect to the RA rate of the signal. It is fixed with respect to the origin of the H1 signal. So this M cap, which is what I am interested in, can be given completely in terms of N0 is fixed. The M cap is divided in theta. But I have that here. I have this thing. So this is how this comes that you see. And this again is an approximate question. It's not the complete story. And then what happens if we have a complete story, that again you will see as well. Now, what I can do now is now write for that delta I can write this thing. Then for H1, I can write this. So this delta I will replace as I mu bar mu. Then this theta H1 I will replace by this entity. Once I do that, this will become, then I will stop there. There is one more thing that one does. Do all this in. I have done one more thing, which is this A theta I have written in terms of its Fourier transform. The Fourier transform of A theta will be to get the visibility in terms of the Fourier transform of, and then I think that up here today. What we will do next is to write this V at two different U and Z and correlate them. Just like we have correlated eta here. Eta at K and K prime and then K prime star. So we will do the same thing here. So V at U and V at V star at U prime. And correlation means that I am doing ensemble average over optical realization. If you look at the right hand side, this thing depends on how the antenna pattern changes at different directions in the sky. There is no statistical, there is no stochastic process there. If you look at the last term, it's just analytical number. The only thing that changes stochastically at different directions is this. So if I write ensemble average of V U and V star U prime, that would amount to an ensemble average here. Eta tilde H1K, eta star H1K prime. So that is what we are interested in. That we'll do next time. So the idea of today was that I wanted to do a little bit more, but the idea is that what is the signal that you are trying to detect? So remember that. Wrote down delta I here, but it argues that this is very small. So not be able to detect it. So we will want to detect the 2-point statistics of the signal. The 2-point statistics of this eta, this doesn't have any 2-point statistics because it's not a function of that. The 2-point statistics is there in terms of the theta. And that statistics is hidden in this function, which is the power spectrum, H1 power spectrum. Theta. And we're trying to figure out how to measure this H1 power spectrum using radio interferometer. That journey, we realized that this is how what the radio interferometer measures. How is it related to the delta I over there? Then if I correlate the visibilities, we get a correlation of this. The correlation of theta is directly related to the 2-point statistics with the power spectrum. That we'll do next time, and then we'll ask the question that what are the caveats in all these? What are the assumptions that have gone in, and how to address them?